Ladies and gentlemen, thanks for coming today to the last installment of the Hackerpraktikum. And with me is Jon from Sweden. Give him a warm welcome. Thank you.
Thank you very much. I actually recognize this knocking on desks. I don't know if it's only in Germany or other countries around here, but I've been to a lecture with a friend of mine in Darmstadt. And that was the first time I heard this knocking on desks. So I recognize what it is. Thanks for the introduction, and thanks for having me here at Hackerpraktikum. These are the 6 topics I'll be covering today. I'm aiming for a 2-hour session with a break in between. I have 150 slides and 3 demos, and I usually make it. So let's go. I'll come back to who I am. I'd like to start by talking about the developer part of the problem in application security, or software security if you wish. Here are some statistics for application security training I've been doing with colleagues in Sweden. We've been asking 108 of our students, this is in industry, so it's not academic education, but educating or training people who are working as software developers in industry. 45% of them who went to our training said they write security critical code. So almost half. This is the years of experience they have as software developers. So the big bunch of them are between 5 or 10 years in professional life. These are the programming languages they say they know. These are typical Java people. Why? Because the training we had was in secure Java. So that's, I wouldn't say that this reflects how many Java versus C# developers there are in Sweden, but looking at the people who came to our training. These are the security areas they've been working in. As you can see, access control and maybe some code audits. That's what they've been doing. This is where it becomes more interesting. 5 to 10 years they've been working in industry. 45% of them say they work on security critical code, and over 70% of them have had no security training at all. This is a challenge. And when we ask them the final question, how is security and privacy prioritized by your product owners in the products you run compared to other things? This is how it ends up. So the first and foremost one is, of course, the features that are required. Next, availability and uptime. Next, usability, performance, maintainability, and then on equal level as features not specified but likely to be wanted anyway is security and privacy. You could go laughing at this and say that security and privacy should be at the farmost left, top priority for all these projects, but that wouldn't really be true. Actually, I think that this is an accurate picture of how priorities should be, but we should not stop before we reach security and privacy issues in software systems. Why did I show this first? Well, this defines what I'm interested in. I'm trying to make sure we do not miss those at the far right end when it comes to requirements in software systems. I'm a front-end developer, which means mostly JavaScript. I used to be a back-end developer, Java, at one of the major Nordic banks. It's called Handelsbanken. We were actually picked as the world's 2nd strongest bank by Bloomberg Markets only half a year ago. And we've made it through the current financial crisis with full strength. We have a very low risk profile, so that's where I work. I'm aiming for a PhD in application security. It's taken me 10 years. So whatever you do, if you go into research, don't leave before you're done, because that will add another 5 to 6 years until you can actually present your thesis. I do some music, which you can find on jonwillander.com. So this is my interest, to push this boundary of priorities in software systems or in software projects to a picture like this. And I've had all kinds of interests and projects in this area where we look into this from various angles. And that's what I will be talking about today. Let's start with my most recent research project, which is RIPE, the Runtime Intrusion Prevention Evaluator. This was published, so this is an academic research paper. I presented it in Orlando, Florida, only December last year. And it's joint work with Nikiforakis and Jonan. RIPE, what is RIPE? RIPE is a deliberately vulnerable C program that attacks itself to allow evaluation of countermeasures. I don't know how many times I've had to explain this, because people think, can I use it to attack other systems? No, it attacks itself. Well, what's the use of that kind of a system? Well, it may very well be the most vulnerable software that's ever been written, because it attacks itself in 850 various ways for buffer overflows. But you could use it, for instance, if you have a compiler patch that's supposed to protect software from buffer overflow attacks. You can compile this testbed and run those 850 attacks to see, did I do well? Did my patch solve all of them or half of them? So we also used it to do such an evaluation. We have 850 working buffer overflow attack forms. I will be demoing how the system works. We have done an evaluation of 8 different countermeasures. And throughout those countermeasures, between 7% is the best, is the worst performance, and the best protection scheme solved 89% of the buffer overflows we have. And it's downloadable, so we have it on GitHub. I actually think I surfed there so you can see. Here we have the source code. Are you familiar with buffer overflows? That's good, because I won't be covering the basics of buffer overflows, so I'm just hoping. Then you might know about stack smashing attacks, where you aim for the return address. So you overflow a buffer and you overwrite the return address on the stack to point it towards your attack code of some sort. So when we're doing this deliberately vulnerable program, the main function that attacks itself has to stay within one stack frame. Otherwise, we're just pushing another stack frame on top of this stack. So this means the function for implementing all of these 850 attacks has to be one function. Just to see how long such a function becomes. And we're going through this. See a lot of cases here for doing attacks on the stack, on the heap, in the BSS segment, data segment. Yeah, we're still at it. We're in one function. Still in one function. Here we're building the payload. Yeah. We're doing some pretty nifty pointer stuff here. I don't know if you're familiar with C coding, but that's a pointer to a pointer to a pointer to a pointer of the target address. So we've parameterized all of these 850 buffer overflow attacks. Just to give you an impression of how it looks. You can go and download it and start doing labs with this whenever you like. A quick look at how RIPE works. We have a backend that performs one attack at a time. So it's a command line where you say, I want to do this kind of a buffer overflow. So typically in the command line in a shell, you can write this. RIPE attack generator, I want to do a direct buffer overflow with a simple NOP sled towards the return address on the stack abusing string copy. And you can change all of these parameters, and it just builds the payload for you and attacks itself to see if it works. And just a quick look at this. I have Ubuntu 6 here. Maybe this is extremely small. I think so. I don't know if you can dynamically change the... Let's see here if I can... Yeah. So this is in an unprotected old version of Ubuntu where all these attacks are successful. And I think we have the exact example here. Yeah, this is doing a direct buffer overflow, this time with no NOP sled at all, against the returner address on the stack abusing string copy. If we run this, we get a shell. And I can, let's see. This is, of course, I'm in that shell, back in this one. I can go here and instead say I want to do this. No, maybe I don't remember all these in my head. We can use a polymorphic knob sled instead. We get a shell again. So we have 850 variations of this working in Ubuntu 6. Then we drive this backend with a Python frontend that enumerates all of these and produces reports of how did all of these 850 attacks go. So this is just how you would invoke the frontend for doing all of these. For instance, retry 5 times, because not all, some of these attacks are quite fragile, so they won't succeed every time, but retry 5 times for every attack. Just to have a look at what kind of attack forms we're looking at. We had an old testbed back in 2003. It was published at NDSS in San Diego. And it became some kind of a de facto standard. A lot of new protections used this to prove that, we solved all of Willander and Comcast's 20 buffer overflow attacks. We have solved the buffer overflow problem. But we felt that, hey, there's more than 20 ways of doing a buffer overflow. We just happened to do those 20 to prove that some other older protection schemes were not doing the right thing. But come on. That was actually the point in time where we decided we should build a really big testbed to bash those protections again. So we added 2 dimensions to this. We added so you can vary the attack code and you can vary the function that performs the buffer overflow. Targets, return address, the old base pointer on the stack, function pointers, wherever they can be on the heap, they can be parameters, they can be local variables, long jump buffers, and also structs with a buffer and a function pointer within the struct. That's the kind of targets we can use. We can do direct or indirect attacks. I think I'll have a picture of showing what the difference is between those. You can choose to do the buffer overflow with a mem copy, string or string n copy, sprintf, stringcat, scanf, fscanf, and even a homebrew loop equivalent of mem copy. You can do this on the stack, both as a local variable and a parameter, on the heap, BSS segment, and data segment. And you can inject shellcode with a knob sled, the polymorphic knob sled. You can create files. You can do a return into libc attack, and you can even do return-oriented programming, which is the latest flavor since 2 years or 3 years back for buffer overflows. And this is the kind of techniques that are actually used for doing, for instance, jailbreaking of iPhones and such. People use these kind of buffer overflow techniques to pull those things off. Also 0 days in browsers where you can actually get to the operating system underneath. Some examples. This is the direct overflow with injected code. So this is the stack smashing attack. The buffer overflow goes this way, from left to right. And here's the optional knob sled that you inject first. Then comes your shellcode, or if you want to create a file, it automatically counts or calculates how many padded bytes you need, and then it has the target code pointer over here, where you get an address back into the knob sled, so you can run your attack code. Here's how that would look in the command line. Some more interesting buffer overflows. This is a C struct, and within the struct you have a buffer, other variables, and then eventually a function pointer. So you can do a buffer overflow within the struct and repoint this function pointer towards your knob sled and attack code. And you can see down here how you parameterize that struct function pointer stack. This is the indirect overflow. So you perform a buffer overflow from left to right. You overflow or overwrite a general pointer, point that one towards your target code pointer, and that eventually will be overwritten itself and point towards your knob sled. So it's a trampoline attack or two-step attack. This was invented by two hackers named Bulba and Killer back in maybe year 2000 as a circumvention of the stack guard protection. And this is a cool one. This is an injected stack frame. So perhaps you have a protection of your return address over here, so you cannot overflow that. Instead, you inject your own stack frame with your own return pointer, fake return pointer that points towards your attack code, and then you overwrite the base pointer. So you actually fool the system to use your stack frame instead of the real stack frame. And there you have the pointer towards your shell code. All in all, 850 working attack forms. I already demoed this in the Ubuntu 6, but let's also look at the best protection system that we had, which was Ubuntu 9 with a lot of protections in it. So let's first do a direct attack with a simple knob sled towards the return address on the stack with string copy. We do that. We get actually a dump here, but you should see further up that actually Ubuntu says stack smashing detected. So it has protection that really detects that this is an attack on the stack. But we also have working attacks against, maybe I have them in the history too. Yeah, let's look here. In the temp directory /tmp/rip eval, we have nothing currently. And then we do a direct attack with a return into libc in a struct where we have a vulnerable buffer and a function pointer on the stack abusing string copy. We do that, and then we again look in this folder, and we have now created a file which proves that we were able to pull off a buffer overflow attack against a modern Ubuntu distribution. So let's look at what we evaluated. We took all of these systems that are supposed to protect you against buffer overflow attacks: ProPolice, Cred, StackShield, libverify, libsafe, libsafe plus, and TED, and then the non-executable memory in Ubuntu 9 and above. Shortly, how this works. ProPolice does a clever thing. It has a guard value here, and it checks the integrity of the guard value before you can use the old base pointer or the return address. So in that way, if you've done a buffer overflow from left to right here, you will overwrite the guard value and you will be detected. It also sorts the local variables, making sure that buffers are always directly adjacent to the guard value. So you cannot do a buffer overflowing local variables. Cred, I don't know if I should go deeply into this, but it's a way of having so-called fat pointers or pointers that you keep with the pointer also a value showing where it can where its boundaries are. So this is a boundary checking add-on for C programs. So every pointer has a base and an extent. So the pointer can start here and never point below, and it can point this far out in memory. So the pointer points into this. And this is a splay tree to quickly be able to resolve pointers, bases, and extents. So when you do pointer dereferencing in your program, your pointer has to stay between the base and the extent. That's how you can add boundary checking to C programs. They also allow that the pointer actually points outside the extent as long as you're doing pointer arithmetics. It's when you dereference the pointer, it has to stay within the base and the extent, because that's when it's sensitive. You're writing to memory or reading memory. So you can calculate with the pointer and have it point anywhere, but as soon as you use it, you have to stay between the base and the extent. That's the Cred protection. StackShield keeps a copy of all stack frames or return addresses from the stack. So as soon as you push a new stack frame on your stack, Stack Shield will make a copy of your return address. And before you pop and use the return address, it checks that you have the same value in the copy and on the actual stack. So this is the way so when you pop stack frame B, it checks the integrity of the return address before using it. Also, it keeps a boundary for code saying that function pointers must point into the text segment. So this is in effect some kind of non-executable memory for function pointers. libverify says all functions has to be in a text segment, but they're copied into the heap where they can be instrumented. So this is a solution with a library. You do not have to recompile your C programs to get this protection. Instead, you just link them to this library, and you get this kind of protection. And they also keep a copy of your return address. libsafe has a boundary. They actually use the address of the old base pointer and say, this is a perfect way to have a boundary of how far buffers can write. We don't have to inject another canary value or guard value. We just say that where the old base pointer is as far as you can write from buffers. Then you have libsafe plus that makes use of debug info. So you compile your C program with a -G option. You get debug info in your output file. That is used by TIED to calculate offsets. So they actually make use of debug info to instrument the code with boundaries for buffers. And then you get that in the binary that you run later. And then we have this one. This has been very famous since it first came out, the non-executable memory. The typical buffer overflow attacks injects attack code and redirects a code pointer towards that attack code. Non-executable memory says that, okay, if you can write to memory, you cannot execute it. You can do either of those. So that effectively makes it impossible to inject code and run it. And this is why attackers have had to resort to returning to libc, because that means you're using libc functions that are already executable, or the more recent return-oriented programming, where you identify segments of code here that you can combine like a puzzle into the function that you would actually like to perform. So these are the results we got. Here's the non-protected Ubuntu 6. As you can see, 99% are successful, 1% partly successful. That's the fragility of some of the attacks not being successful every time we execute them. And it goes up. So with libsafe, you get 7% protection. Libsafe plus 19% goes all the way up. And with Ubuntu, that has both ProPolice, it's the same system as here, and this non-executable memory, you protect against 89% of our 850 buffer overflow variants. These are the top 4. I don't think I put them here in the slides. If you want to go deeper into why the outcome was this way and what kind of attacks were actually successful against these protection, you can just read the slides, because you got information here about every one of them. And of course, there's the full research paper too. Instead, we'll move on. I'd like to talk about modeling, visualizing, and pattern matching security bugs. By the time we had done this, we'd started working on buffer overflows. I'd identified the problem that programmers need to know about these things. They need to get reports about this to be able to write better and more secure code. We got into this. How can we model it? How can we visualize it? How can we report back to programmers about these problems? This was published at a workshop in Pittsburgh, and joint work with Pia Falk. We quickly noted that most of the static analysis tools that were out there, they gave some kind of, they had textual models of what kind of security bugs the tool should look for. So this is a specification. You had to understand how to make models like this, and you had to read them to understand how, okay, this is some kind of tainted data that's copied from the user, and it flows, and then they're used in a dangerous index of an array. This is a I would say, rather complex model of security bugs to look for. But even more complex was the reports that programmers get back. This is a dump from where I deliberately implemented a buffer overflow, run a static analysis tools that reported you got a buffer overflow. So we're actually saying that programmers should understand and like these kind of reports and know that, okay, I need to go and fix my code. Imagine doing this for a 200,000 lines of code system and getting these kind of things that's barely readable as this is, but for that amount of code. So we thought about maybe we could do something that's graphical and more tangible to both model and visualize security bugs. So we started looking at something called program dependency graphs. Have you heard about such things? They're actually quite a cool thing from computer science. They were originally invented out of two requirements. But first you have the compiler guys. Compiler guys are always into optimizing. So they wanted to know what kind of dependencies between statements in code do I have? And if there's no dependency, I can reorder them. So I can put the right stuff in the pipeline in the processor, and yeah, those kind of optimizations that compilers typically do. The other guys were the ones looking at new ways of debugging and helping programmers. And they invented something called slicing, where they thought that if I could take one variable deep down in my code, maybe I already know I have a problem. This variable becomes null, and I don't know why. How can this variable become null? You pick that statement with your variable, and you call it your slicing criterion. And then you tell the system to slice out the program that can affect this variable. So you do not have to analyze the whole program. You only analyze the slice that can eventually affect this line that I'm interested in, that I have a bug in. And this was a very beautiful idea. But it so happened that software is so interconnected and complex that you often got in return 80 to 90% of your system. If you go deep down into software and point out one variable and say, give me back only the code that can affect this variable's value, you often get 80% of the system back. That's how interconnected software is. So the original research idea was not really successful. But they invented these kind of dependency graphs, and they were successful. They have two types of dependence. The first one is data dependence, meaning that here we have some user input and a dotted line or arrow saying that here we use the data, so this node in the graph is data dependent on this one. Here's a little snippet of code for you. We have a function that has user input here, and that's used over here to assign the var variable a value. So this the var variable has a data dependence on user input. So when you build a graph that models the system, you will have these kind of edges between any two nodes that have a data dependence. The other kind of dependence is control dependence, meaning that the first node decides whether the second node will be executed or not. Typically conditional nodes or conditional statements. So the if statement here, you can see it over here, depending on the outcome of this node will be executed or not. So this one is control dependent on this node. With this kind of formalism, you can actually model whole systems. And if two nodes do not have a dependence on each other, it doesn't matter in which order they're executed, because they cannot affect each other. So this is a quite cool model of software systems. So we thought about this. Can we model security bugs with this kind of formalism? Even look for them in such graphs? Even report back to programmers that you have a blah, blah, blah dependence between these two nodes? So we looked at input validation. It's a kind of generic problem in software security. And you would model it like this. You have some kind of an external input. This would typically be called a source nowadays. You assign some kind of variable with this. So you collect the data. This could be from an environment variable, from a network device, or a form field, or whatever. Then you have a data dependence to a validation. You have a data dependence to a use. This is the sink. And you also have a control dependence from the validation, meaning that the validation controls whether this data can be used or not in the sink. This is actually a high-level model of the input validation problem. So we started using this for searching fairly large software systems for flaws that did not do input validation correctly. Of course, you could always dig deeper and look at this. Is it doing the right validation? Just because we have a control dependence here doesn't mean that we're doing the right thing over here. But if we're not even having a control dependence there, we definitely know that we're not doing input validation. So this is just to explain how this flows. You got user external input flows. You have a data dependence to the first node there. You have a data dependence to the usage, the sink. You have a data dependence to the validation, and you have a control dependence in the from the validation to the usage. Do you know about double free, the double free bug? Not so many nods. In C programs, you malloc memory on the heap, and you free it when you've used it up. In fairly complex systems, you at times end up freeing the same memory twice. And that was just a bug that typically caused a segmentation fault, and people felt that, one of the things that happens in C programs. We have to try to get away from the double free or triple free. But then people started noting that there's in-band information on the heap on how large these chunks of allocated memory are, and where they should be chained to each other so that we can keep track of them. So if we free memory once, have some code in between that can write to that memory, allocate it again, and try to free it a second time, we can inject that in-band information and make the second free actually overwrite any kind of memory, which of course would be the return address or some other code pointer, and point towards our attack code, and bam, we have a buffer overflow again. So that's the double free in a nutshell. It can be used for arbitrary code execution. So this is the program dependence graph model of normal use of free. We call free, and we have some kind of a pointer that points to the memory that we want to free up. This is a model of the double free problem. We have two calls of free, and we have a data dependence between these, meaning that we're using the same data for two calls of free. Are you with me? I think so, yeah. So we want to detect correct use of free. We started out that. Can we prove that a program is secure in this sense, in the sense of free, by looking for the pattern of free usage? Turned out no. Why? Well, because the bad pattern contains the good pattern. If we only look for good programming practice here, we will get the result that, yep, someone is freeing up memory, looks good to me. So we actually have to look for bad programming practice. We have to search for the bad graph to be able to detect this problem. So let's move back to, I'll go back here. So I can just mention this. This is, I pointed it out up here. This is a model of good programming practice. Here we can look for, if we search the program for this graph, and we don't find it, we know that we have external input when we have a sink, but we cannot find this pattern, we know we have a security bug. So in this case, we have to search the graph for good programming practice. And in the case of double free, we have to search the system for bad programming practice to detect the security bugs. And this is interesting. This means that in static analysis, we actually have to look for both good programming practice and bad programming practice if we want to report back problems to the software developer. Then we thought maybe we could lift this to yet another level. Because when we talk to software developers about using static analysis tools, they always said, well, I got a bunch of reports. I got 2,563 security bugs. Okay, maybe I'll fix them. But you gotta tell me where to start. Turns out it was a total flat report. No priorities at all. Nowadays, you typically have a severity. It says 4, 3, 2, or 1. So you at least know where to start. But they want to know the top 10. How can we report back to them where to start? If you're going to just have time to fix 10 security bugs out of those 2,600, which 10 should it be? That's a really tough question for static analysis. So we try to do something about it. We try to come up with some kind of a severity measure. So these are, I'll show you some graphs that we would propose go from high to low in the input validation example. So this is the worst case. Let's say our search engine finds this pattern. It finds a source, a usage, a definition of it, and a usage in a sink, and no validation node at all. That's a total moronic software. No input validation at all. A little bit better, but not really good, is a source, definition, some validation, a sink, but no control dependence. That means that there's a possible execution path to the sink without passing the validation. Now we're getting to less and less severe problems. A source, definition, validation, but we're doing a narrowing typecast. We're losing information here. Or you could even say that the sink has one view of this data, the validation has another view of the data. We're still having the control dependence, but this is not a proper validation. And this is just the other way of doing it. You have a narrowing typecast to the usage, but not to the validation. And just to give you a glimpse of how this could look on a more concrete level, and then this is actually has a connection to real problems. You have some incoming XML. You demarshal it, so you get some kind of a model in memory. You do DOM parsing before you validate, but you do SAX parsing before you use it. So you're actually validating one view of the world and using another view of the world. And there has been some really severe security bugs having exactly this pattern. I can see someone nodding over here. Is it the signature validation in the Office package? Yeah. Sorry? Okay, yeah, but okay, then they've just had the same problem. Yeah, because this was a problem also in the Microsoft Office suite, where you did a cryptographic validation of the document. The validation did DOM parsing, but then you used that element from the document with SAX parsing. So that's, I think that's it for the modeling and visualizing of code. And I have intended for a break here, where I will also switch T-shirt. Have you seen this? So let's take a break until 5 o'clock. Okay, back to application security or software security, as it was named when I started this out. Just a short, this is maybe the most theoretical part of my talk, but I wanted to add it to my talk because this was a big moment for me when I got some feedback on a paper I had written, saying, just in the review comments, you should look into safety and liveness. At first, when you read that kind of a comment, you feel, how many papers will this be that I have to read now? But it turned out this is really cool, safety and liveness. So I'll just mention it and show some stuff, and I think it puts application security into perspective. What I was asking myself was, can we build some kind of an execution monitoring program? It's nice that we have an antivirus guy here, because actually, in formal terms, antivirus software is execution monitoring. At least if it's doing stuff runtime. Maybe not signature matching, but if it tries to monitor the execution of a program and detect that something bad is happening, we're doing execution monitoring. So can execution monitoring, can a system overlooking the vulnerable system solve the software security problem? I was thinking about that. Is that possible? And does that mean that we can analyze software and even test software at compile time so that we know that what we deploy is secure or fairly secure? That's where this came in. I wrote a paper on it and I got the feedback. You should read about safety and liveness. I guess you're more familiar with these two terms, blacklisting and whitelisting. You hear about them very often, and the typical saying goes that, you shouldn't do blacklisting, you should do whitelisting. So in this case, in blacklisting, you build a model of bad stuff. In the case of whitelisting, you build a model of good stuff. Then you move on. With a blacklist case, you pattern match inside the model and raise alarms as soon as you get a pattern match. Whereas in the whitelisting case, you detect execution outside the model and raise alarms. This means that if we try to do a graphical view of this, you have blacklists and whitelists. You have a model of abnormal behavior, you have a model of normal behavior. You will find this, for instance, in intrusion detection systems, you have misuse detection, anomaly detection. You find all these words, and this is what it's about. The interesting part is that we always detect bad things. No matter what we have been modeling, we have to detect bad stuff. So if we have a model of abnormal behavior, which is a blacklist, we will detect within the model. If we have a whitelist, which is a model of normal behavior, we will detect things outside the model. So software security, is it all about avoiding and detecting bad things? Can detecting bad things solve this problem? Not formally. Here comes safety and liveness. This was defined in 1977 and the early 80s. So this is the oldest results I'll be talking about today. Safety properties of code say that no bad thing must happen during execution. And interestingly, it says also the bad state has to be discrete, meaning that if you're doing execution, you can have a state machine and a transition between two states. And you can know that if I move from this good state over this edge, I will enter a bad state. The step is discrete. So I can also have an execution monitoring system saying that I am not allowed to take this transition because I will end up in a bad state. I will prohibit that transition. Tell the system you're not allowed to do this. That means it's enforceable. Safety properties of code are enforceable with execution monitoring. The execution monitoring system can prohibit transitions into bad states. Liveness properties, which are the other way of looking at software properties, say that a good thing must eventually happen during execution. Why do we need those liveness properties? Well, if we only would go with safety properties, the best software system on earth would be the empty system. Nothing bad will happen, no code. But we do want things to happen, namely the good things. And that's why we build software. So we have liveness properties. A good thing must eventually happen. Interestingly enough, such properties are not enforceable via execution monitoring. Because the execution monitoring software cannot know if the good thing will happen eventually in the future. So there's no discrete state where the execution monitoring system says, oh, I now know that the good thing will not happen in 5 minutes or later. Oh, maybe it will happen. Oh, sorry. There's no way of an execution monitoring system to enforce good things to happen. If we could build such a system, then we would be off, and we could all leave the lecture hall and go and have beers already now. So let's look at this. This is from just showing that there are both sides of software. In safety, you have access control, enforcing that only people with these capabilities or these roles in the system can access these functions or this data. Mutual exclusion, the bad thing defined as two threads executing in the critical section at the same time. So we can have an execution monitoring system saying that, I already have a thread executing in the critical section, so you're not allowed to do it. I enforce the security policy upon you. Deadlock freedom, the bad thing is deadlock. So that can also be enforced by an execution monitoring system. On the other side, liveness, starvation freedom, sorry. Here the good thing, we're defining good stuff here, is making progress. And we cannot build an execution monitoring system forcing the software to do things and make progress. That's not possible. Availability, now we're getting into security. If you define availability as guaranteed service, there's no way of building an execution monitoring system guaranteeing service. Let's say we build a web application. We have a security requirement that it has to reply to all requests within 30 seconds or something. There's no way of building an execution monitoring system that enforces that application to actually comply and respond within 30 seconds or 3 seconds. What should the execution monitoring system do when those 3 seconds or 30 seconds have gone? There's no whip to force the system to behave. And also, of course, you have the very classical issue of termination. You cannot enforce a policy upon a software to be sure that it will reach a termination state. That's the termination problem. So just to go back to this, if we have the same view that we had on whitelisting and blacklisting, we can here note that we always detect violations of safety properties. And that's the only part of software security that we can actually solve by having something looking or enforcing things upon software. Some kind of a fundamental limitation of what we can do. So that's my aha moment doing research. We have to stick to safety properties if we want to enforce them. Result. Final part. I just thought that if I'm going to Hackpra and all these super great speakers, I mean the lineup so far has been stellar. I know several of these people and they're just doing totally great stuff. So I have to bring something that's related to web. So let's do cross-site request forgeries. They're currently my favorites. So we'll do them against RESTful services, and we'll try to do a live demo of a multi-step, semi-blind cross-site request forgery. Starting out with the RESTful ones. This is my picture of what a cross-site request forgery is. I'm guessing you're familiar with them. You are? And that they've also been called session riding, meaning that you reuse or abuse the victim's active session to perform forged requests. And this would be maybe a more realistic view of it. You have to somehow make the victim visit your site, and that site in turn forges requests and reuses the session. So for instance, you could be logged into your favorite online shop, but not actually doing any shopping. You could have the remind me cookie set 2 weeks ago. You have an active session. And you visit a malware site that issues a request to that online shop, and your session cookie will be included. So let's say we have a small chat system, and I type in I love OWASP, because I do. I love OWASP. So John says, I love OWASP. Is it possible for another system to say, I hate OWASP, and post that in my name so that John says, I hate OWASP? Yeah. Cross-posting is possible. I don't know, have you seen it?
Yeah, we actually had this topic in the last lecture of our Hackpro.
Good, good. So you know that this is possible. And I also have some example code here, so if you want to look into that, it's actually possible to cross-domain post things. Here's an example of how it could look. And there used to be a protection in Web 1.5. I call it 1.5. I don't know if there's such a term, but... So maybe you had a wizard-style checkout process on your online store. So you had to type in your shipment info, and then you went to another page where you would type in your payment info, and maybe would you like this extra offer? You have a final, yes, I really want to buy this. So a multi-step purchasing. And there would be a token that you got when you visited this page. You got a token that had to be submitted to be able to do this. And that's the classical anti-CSRF protection. So you will have a multi-step process, and the state is built up in steps, and you have a server round trip between all of these states. This is the Web 1.5 version of doing it. Shipment info, payment info, yes, I really want to buy this, oh, here's the result page, we're shipping this within 24 hours. And you're building up a state on the server in multiple steps. And the attacker couldn't forge the last step without a valid token from all of these. Right? But we're building rich internet applications nowadays. We're not building these Web 1.5 stuff anymore. So now the purchase process is client-side. It looks like this. You're on the same page. You're building up some JSON. You're adding your items, adding some more items. You're adding your shipment info. You're adding your payment info. We're still on the client. We haven't sent a single request to the server yet. And then bam, in one request, we dump all of this data in. And now we're in a state where we cannot tokenize these steps anymore. There's no server round trip. There's no ticket for going to stage 1, 2, 3, and 4. We're just building up a massive state client-side and dumping that JSON into the server. So the question comes to mind, can an attacker forge such a JSON structure? Is that possible? I mean, we've seen that we could cross-domain post forms, but forms are URL encoded, and they're defined as forms. Sending in JSON to a REST interface, that's another story. So this is what we would like to do. Build a page that does a cross-domain post, and that will add the session cookie from the victim and send in a JSON structure instead of a form. Is this possible? Let me show you how. I was working on this. It took me a weekend, and I did interact with some of the other famous hackers. Maybe you've seen some of them during the Hackpra sessions. We were discussing this. How should we go about solving this problem? So this is the regular form. I've left some spaces that we'll fill out. So we'll do a post. This is on the malware site. We're doing it against some kind of a vulnerable system. And this is the typical input form field that we will fill out with the data we would like to cross-domain post, and then some kind of submission. Now we have to transform this formalism into something that could dump in JSON to the server instead. Okay, we start by making it invisible, because we don't want people to see that we're actually having a form on the malware site. So that's the easy part. Then comes this one. This is interesting. Turns out that forms in the HTML spec allows you to change the encoding type into text plain. So now we will no longer dump in a form encoded, URL encoded data to the server. We'll send in the encoding text plain. So this will mean that we will produce a request body that looks like this. It will have the name and the value from the form in plain text. But that is not valid JSON. So what we do now is that we add the JSON in the name part. And then we just comment out here and add a dummy as the value. You saw, let's back up. This is what we will produce. We will produce this little equal sign, and that could be a really bad part. So we need to get rid of that, because in valid JSON you cannot have equals if it's not within quotes. So that's why we put the JSON in the name, and then we comment out the rest. This will produce a body like this. Open up, comment out. There comes the equals, and there's the value actually of the form we're sending in. So this is maybe the weirdest form field you've ever seen, but you could do this. And you do it with encoding text plain. This is acceptable JSON. For instance, for the very popular Jackson parser in Java. So let's do this. Now I have to resize this. I have a little demo system here. It's a chat. So here we are. I'll just switch user here to Mr. Bad Guy. So I'm logged in as Bad Guy here. I can see hi John, and it turns up here, and here I'm logged in as John in Firefox. This one has a REST interface in behind it, so I'm running on a local server here. Let's open up so that you can see what we're doing here. Vulnerable one-liner resource. Here you have the. Maybe I can. This, I don't know, is it too small for you to see? I think I can do it like this. The editor. Doesn't allow me to. Big screen. Maybe I have to save. Then I can edit this. Let's see, that's bigger. And we double click this. So I have a Java implemented backend here. I put new one-liners. I get the cookie parameter to see which user it is. And then I actually use Jackson parser. I don't know if you can see it or if it's deeper down in the code. This is just to convince you that I'm not using a regular web application with forums here and pretending that I'm doing JSON stuff. So let's see what Mr. Bad Guy can do. I should probably increase the size here. So he will tell me that he loves JavaScript. Can you see or see what this one will actually do? It will inject an image with source 1 that will typically provoke the on error to be triggered. And on error will say get to the nickname cookie If the nickname is not bad guy, change the nickname to moron. So let's see what John has to say about this. Bad guy says this. Turns up like, I love JavaScript, and now my name is moron. So I was cross-site scripted, and this was sent with JSON back to the. So it's a combination actually of cross-site scripting and cross-site request forgery. And of course, I can get back to the bad guy. It's ECMAScript full. Did you see what this one does? Installs a keylogger. Hopefully it works. And we have the log here, down here. And let's see if it works. Hi there. I get some SSL exceptions here. Maybe not. I should see if I get an error here somewhere. I get a lot of errors here. Maybe I'll have to do this. Let's see. Attacker. I might have, yeah, this is the, I have my own self-signed SSL search, so it doesn't really like me posting and sourcing in scripts from there. So let's reset that one. Go here. We try again. Yep. So I don't know if you can see that. But I have a keylogger installed, and it's dumping in all characters that are being written. So it's an easy keylogger with cross-site scripting, nothing else. And you just capture the characters that are typed, and you do images to dump in the characters. Okay, that's cross-site request forgeries against RESTful interfaces. I should point out that I deliberately did things in. Let me think. When you're dumping in this kind of JSON, it doesn't really work from Chrome. Why? Because they add an on boundary to these. Maybe I could even do it like this. Attacks CSRF. Here's I just have a little pig here. Yeah, this is a good way of showing you what I mean. You see, I have the encoding text plain, but WebKit actually adds a semicolon boundary equals. And that is not acceptable for the incoming Java system as an encoding. So this kind of JSON attack is only possible from Firefox out of these three that I've been checking. Maybe working in Internet Explorer. I have a Mac, so and maybe working in Opera. I don't know. That's for you to find out. So that I promised myself to be honest. So I told you that it's working in Firefox. So this is just important points for you if you're writing REST APIs. You need to restrict your HTTP method to post if you're actually accepting incoming stuff and changing your state on the server. That's just being true to the HTTP spec. You should restrict to AJAX because you cannot forge cross-domain cross-site request forgeries with AJAX headers. So that will actually prevent this. And you should definitely restrict your media types to application JSON and not accept text plain. That would solve this problem. So we're reaching the final part, the multi-step semi-blind cross-site request forgeries. We're back to this token stuff again. It seems like when you read documentations about cross-site request forgeries, for instance, on the OWASP website, but also in other places, You always see examples of attacks doing a one-off. They're doing one request and fulfill the full attack. Also, cross-site request forgeries are explained as blind because the response comes to the victim's browser and not to the attacker. So the attacker can never parse or read the response and build some kind of a next step upon the response. So it's often been explained that cross-site request forgeries is a one-request attack against an interface. In some places, you do see a comment that splitting it up in multiple steps will not save you, but never really any explanation of what they actually mean with that. So I had this question in mind. Could we do something here? It was around about Christmas last year. So we were building up state in multiple steps if we had this Web 1.5 solution. And we could not do forged requests to the last step because we had to do these first steps. But if we do not have tokens that restrict this, but only have a wizard style that has multiple steps, can we do a multi-cross-site request forgery against this? Can we time this so that we do the step 1, wait for it to be fulfilled, then do another, and wait for that one, do another, wait for that one, do another? Is that possible? So it would look more or less like this. This is what I had in mind Christmas Eve. A multi-driver HTML page, which is the malware page. It would have an invisible iframe, and it would perform the first stage of this multi-process checkout. It will wait, then invoke another invisible iframe with the next step of the checkout, wait, and do the next step. So this kind of. So I was asking myself, is this possible? Here's the solution. We start out with the first, there we are. The first HTML page here. This is an example of extra easy CSRF because it's done with a getter. So you just, this is the first page you will have in your first invisible iframe if you want to do an CSRF get. And you include the iframe getter.js. I'll show you that one very soon. And on body load, we say iframe getter on load. Here's the code for the iframe getter. It has a report and get function, which is set interval. Yeah, so you do an interval with 1,000 milliseconds. Every second you do a report and get. Report and get. You build up an image element, and you also report back to the parent that who you are and what you're doing. So you for every if you haven't done the image tag yet, you say, have I gotten the first step, past tense of get? I will perform this. I will build up the image element and inject my HTML inside there. And then I will clear the interval. This means that typically when you do a cross-site request forgery with an image tag, you will not get an image back. So you will get on error. And we use on error here to actually trigger and tell the parent page that this part of the attack is done. You can now do step 2. And that's what I mean with semi-blind. You've always heard that cross-site request forgeries cannot be, the response cannot be seen, but actually we can see that the request is done, because that's when we trigger on error. So we wait for the get, it's over when the on error fires. Here you see, you set the attribute for on error, and we clear the interval of telling the parent page that we're still doing the attack. Here's the example of doing it with a post. So we have sourced in the iframe poster, and here we of course need some kind of a form. We're pointing out here some vulnerable site, the add basket. It's an invisible form. We add the parameters that we need, maybe the goods ID or number of items, the country, proceed. Here's the iframe poster in terms of JavaScript. So how do we do this semi-blind in the terms of post? Well, we set up an interval of reporting every second that we're not done yet. As soon as the post has been performed, the iframe will actually load the response of the form post, meaning that this code will be cleared out, and the parent will no longer get the reports of once a second, I'm still working. So the parent in itself has another interval looking, have I got a heartbeat from the poster yet? As soon as the heartbeat dies out, I know, okay, I've done posting. I can now move on to the next step. So we wait for posters we wait for these messages to stop coming to the parent, then we know the post is done. And just the multi-driver, I don't know if you want to go through this, but see, we just specify here, this is in the parent malware page, we just specify our HTML for the iframes, and they have some figures here for knowing if this step is done yet. They have an ID, so we know we do this one first, and this one. We could add as many as we like here, depending on the checkout process, how many steps it has. And then we append iframes with this code. We can decide if we want them to be hidden or not. I will show them, so we will go false there. And here's just for the code for checking the heartbeat. So we go from no, maybe, to yes. So in 2 steps, we check, has the post been done? Should I proceed with the next invisible iframe? And here's just a receiving message. So this is the iframe post message functionality that you might know about. Okay, so I'm about to demo this, but I will do it against real sites. So I would prefer if we do not record this. I have not reported to them that they have a problem. And these are sites that I have been spending a lot of money on myself. So I have also in these demos avoided the last step because I do not really want to purchase these things. So let's do this.